Right, so here's what we were talking about last time. We're talking about symmetry, and I always forget to check that. 2 seconds, let me pull this up again. Wrong course. Hang on a second. Pulled up my Math 216 notes. Here we go. Okay. Okay, so here we go. So last time we were talking about symmetry. Flashback to an old theorem from single variable calculus. If a function is odd as your integrand, and if the domain is symmetric in the sense that, when you reflect over the origin, it doesn't change. Said differently, the upper bound and the lower bound are negatives of each other. But let's reinterpret this as a symmetric domain. Then the nice punchline is that the integral is 0. Right? Awesome conclusion. We didn't have to do any actual anti-differentiation, which is a very, very convenient fact. Okay, so the big observation I'm making in this few pages of notes is that you can do the same sort of thing with a double integral. And so, reminder: this is why the single variable result works, because when you look at the Riemann sum and you look at the terms inside of the Riemann sum, this term here and this term here that we're, for geometric convenience, interpreting as areas, right? Those two terms are negatives of each other. Just because they have the same width and opposite heights because of the oddness of the function. They pair up because of the symmetry of the domain, and everything just cancels in a puff of smoke, right? So integral is 0. Okay, so you can make the same kind of argument in a two-dimensional setting. Again, we've done this last time, so I'm going to go a little bit more quickly than I did Monday. But you can talk about a reflection over a line, and it's exactly what you would think it is, right? Given a point x, here's its reflection. All right. With that idea, you can define corresponding notions of oddness. Here's what it means for a function to be odd. That you get a minus sign, right, when you take a point and compare the value there with the value at its reflection. Same idea. Just like an odd function in single variable calculus. You can talk about what it means for a domain to be symmetric. Domain is symmetric if whenever you have a point in that set, well, its reflection is also in the set. It's a Rorschach type situation, in other words. So here, for example, is close enough, but you get the idea. And so the way I would characterize the fact, my attempt to suggest artistically that this is a symmetric set is that, well, whatever's happening on the one side is also happening on the other side. So whenever you have a point in the set, the reflection also in the set. Thus this idea. Okay. And here's the resulting theorem. And this is where we ended last time. If a function has odd symmetry, right? If the domain is symmetric, then the integral is 0. Morally equivalent reasons. So, here's again, here's what a Riemann sum looks like. This is what an integral looks like with a limit, right? And just look at the pieces. On the one hand, this piece there, click the wrong one. This piece here, right? This piece here at the reflected point, because of the oddness, these are negatives of each other. And they cancel in the summation. Right? So this green piece cancels with that purple piece. Every other green piece cancels with every other purple piece. Everybody cancels with somebody else. There's nothing left over. The summation is 0. Okay. All right. Same idea. Now, a couple of quick warnings with this theorem. You got to be ultra careful in applying this theorem. because if you apply this theorem, if you find yourself faced with an integral to compute, right, and suppose you cite this theorem of, hey, these conditions apply, and therefore the integral is 0. And let's suppose that you're wrong. Then nothing you've written down is both true and relevant to the solution of the problem. It just isn't, right? I mean, if you cite symmetry when, let's say, maybe the domain isn't symmetric, then there is no solution to the question that involves symmetry. So having correctly observed, for example, that the function has odd symmetry is irrelevant to the solution of the problem. Right? So that's the danger. The danger in applying this symmetry theorem is that if you apply it incorrectly, then nothing you've done is relevant to the solution to the problem at hand, and it's real hard to come up with ways to rationalize giving partial credit. So the moral of that story is just be careful. Just make sure to check both of the conditions. Make sure to always think it through when you apply a symmetry theorem. And we're going to see several examples coming up here. But both of these conditions must apply. What I see all the time happen on exams is for students to see a nice, pretty symmetric domain and just sort of figure, oh, look how symmetric that domain is. The integral must be 0 by symmetry, but they forget to check whether the function's odd. Right? Or vice versa. They see that a function has odd symmetry and just they're so excited about the fact that this is true, they forget to check whether the domain is symmetric. So anyway, you've been warned. Be very careful. You've got to check both conditions. Furthermore, the line. It's got to be the same line. It's no good for a function to have odd symmetry over one line and for the domain to be symmetric over a different line. Right? You look at how the cancellation argument works. Let's see. Where did I put the... here it is. Yeah, right. How the cancellation argument works. The symmetry line for the domain is what makes these terms pair up. The symmetry line for the function is what makes them actually cancel. And you need both of those to make the Riemann sum disappear. Right? So you can't sort of mix and match your application of these conditions. It's got to be over the same line. So another really common mistake. It's really easy to mess that up. So apply this theorem, wonderful and powerful and quick as it is at doing its job. Answer 0. It's very, very quick. Apply it carefully. Okay, so let's see some examples. Here's a question. Suppose we're computing an integral over this unit square. Right? And I want to compute that integral. Again, don't move too fast and say, hey, this is symmetric over that line. Integral is 0. Whoa, slow down. We haven't even checked the integrand yet. Right? And by the way, it's symmetric over a lot of lines. Which line? Symmetric over all those lines. Okay, so we have a symmetric domain. Now, here is our integrand, x minus y. We would do an integral over this square of this integrand x minus y. Can we apply a symmetry argument? Now, if you're a little too fast and loose with this, there's a temptation to look at that line and say, look, we have symmetry over that line, and boom. Well, the problem is this function does not have odd symmetry over that line. So that symmetry argument fails. Right? Okay, what about that line? Well, same thing. Right? However, over this line, everything works great. So the domain is symmetric over that line. Right, and now let's check to see what happens with the integrand. And now, how do we decide if this function has odd symmetry over that line? Well, we've got to figure out what the formula is for reflection. There you go. Now, this is a little geometry problem that you have to deal with every time you apply a symmetry theorem. You have to ask yourself, what is the formula for reflection? Given a point at coordinates x, y, where is its reflection over this specific line? Right, y equals x. In this case, that's we're applying it here. So now in this case, it can convenient line. It was not hard to write down the formula for the reflection. If the line is not convenient enough to be able to conveniently write down the formula for reflection, then hey, maybe a symmetry argument's not such a good argument after all. So good news, the symmetry lines that we tend to encounter tend to be relatively convenient lines. Nevertheless, you got to write down the formula for the reflection. Okay, that reflection then, that is what you have to plug into F to confirm that you get, F. Let's see here. F at the reflection, and compare that with F before the reflection, and get this minus sign. Okay, and you got to actually plug in the algebra. You got to do this whole thing out. You got to, write down what your reflection is. Evaluate this function f at the point y comma x. This can be really confusing. It's very. Let me sort of walk you through why this is awkward. When you say f of y comma x, there's this temptation to think that is this thing, but it's not. This is the first entry in the function. It goes wherever that thing goes. That thing goes there. Right? So y, being the first entry to this function, according to this formula, the first term that's written as x is y. Right? So be careful. Right? And then likewise, this thing here, we're calling it x, but what it really is the second entry to that function, which means it does whatever that thing does. Namely, it goes there. So f of, given this function, f of y comma x is y minus x, not x minus y. Okay, and then you observe that this thing truly is the negative of this thing. Okay, so function has odd symmetry, domain symmetric over the line, integral is equal to 0 by symmetry. Everybody see how the argument works? Okay, yeah.
Can you explain again how you got r of xy equals?
Yeah, it's just a geometry problem. So in this case, I guess I didn't really quite talk about that, but if this is the point x comma y, let's think about this sort of structure that connects to it, right? That distance is x and that distance is y. If you flip that point over the line, well, let's flip this entire structure over the line. It'll look something like that. Well, if that distance was x, then that distance is x.
So it's specifically because you chose that line?
It's specifically because we're reflecting over this line. Yeah, so this formula for the reflection is specific to that line. And anytime you apply a symmetry argument, you got a new line, you got to find your brand new formula for reflection. Good news, we use that line a lot. So feel free to memorize this one. All right? Likewise, we'll reflect over the y-axis or reflect over the x-axis, this kind of thing. So you just kind of memorize those. Here's this next one's going to be over the y-axis. Reflecting this. Oh, let me get it. I'm getting ahead of myself. So this domain, this triangle, we note that it is symmetric over that line. Let me quickly observe while we're at it, by the way. That's the only line over which this domain's symmetric. So this is it. This is our only option. Back when we were looking at the square, we had a bunch of potential maybe this line, maybe that line, maybe that line, whatever, right? Here, we only have one candidate line because of the very few symmetries that the domain has. Good news, it's easy to write down the reflection over that line. Right? The reflected point has the same y-coordinate as the original point. The x-coordinate is just the exact negative of what the original x-coordinate had been. Right? Easy formula. Everybody on board? Warning. Warning. There is a strong urge, at least so it seems, based on what I've seen a lot of students write down on their papers, to think, we're reflecting over the y-axis, so the minus sign must go on the y. Nope. It just doesn't. So don't step on that landmine, please. Right? I mean, I get the allure. It's the y-axis. We're reflecting y. It's got to be y that gets the minus sign, but it just isn't. So make sure you see the picture. I mean, the picture makes it clear, right? Don't inadvertently remember that wrong. Think it through geometrically every time. The picture tells all. Beware. Okay, so, and then same sort of a thing. This formula for reflection. Plug that in. Compute, 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 and notice you do indeed get a minus sign compared to the value of the function at the point from which you reflected. Yep.
Do you have to prove that a domain is symmetric?
No, so with domains, it's usually sufficiently what I'm going to comfortably call clear. Yeah. So with when you cite, I have some rules about what I need you to write down, and let me go through those in a minute. But yeah, it's a great question. Yeah, and I will address that. Okay. Okay, is everybody happy with this question? Should we again use symmetry? I did go a little too quickly over. So this function I claim has the odd symmetry, and so that calculation is to right here, right? You plug in the reflected point. Here's the reflected point. You plug that in. Out comes this expression. See if I can get this all on the same page. There you go. Roughly speaking, what happens is this minus sign that comes from the reflection goes in there and gets cubed. And roughly speaking, the point here is that -1 cubed is -1. That's why you get the necessary negative. Yeah, everybody on board? So you can kind of see this in advance. You do have to give me the argument. You have to write this all down. But you can kind of anticipate it without writing it down and saying, oh yeah, if I can get a minus sign on that x in that formula, that minus sign is going to get cubed and turn into a minus sign, which is exactly what we need. Everybody happy with that? Yeah. Okay. All right. Okay. So integral 0 by symmetry. Here's another one. Let's suppose we're using the same domain, and suppose this is our function. And here's what happens a lot. And again, I see this all the time. It's so tragic to see this. But I will see students say, oh, look at how lovely that function is. That looks highly symmetric. And the domain we've already agreed is symmetric. I got a symmetric domain. I've got a symmetric integrand, integral 0 by symmetry. It's wrong. Oh, it's such a tragedy. Because nothing the student has written down, nothing that I just enunciated is both true and relevant to the solution of this problem. So the domain is symmetric. That's true, right? This domain still got a symmetry over the y-axis. But the function only has one odd symmetry, and that's when you put a minus sign on the y, because y has the odd power. And if you think about it, a minus sign on the y is a reflection over the x-axis. So these are not, even though each of them is symmetric over a different line, there is no single line over which both the integrand and the domain are symmetric. So there is no symmetry argument that you can make to do this last example here. This is the landmine question. Don't step on the landmine. All right? Everybody happy? Okay. So let's talk about, to answer your question, what do you have to write down on these? I think this is the last example I had. So what I would like to see, if you do a symmetry argument, is the following. I want to see what is the line over which you're making a symmetry argument. Explicitly tell me what the line is. You can say y-axis. You don't have to say x equals 0. But you get, by some reasonable form, tell me what line it is. You got to write down the formula for the reflection. You've got to show that the function is odd. And you have to assert correctly that the domain is symmetric. You don't have to prove the domain is symmetric. It's usually geometrically pretty clear, right? So these are the 4 things that you got to give me. If you give me those things, then you are welcome to say, ergo, this integral is 0 by symmetry. Okay. Everybody happy? Now, why won't I allow you to just say, well, integral zero by symmetry? And the answer is two things. First of all, this is a class about reasoning. It's not a class about correct answers, right? So that's the one. If you say it's zero by symmetry, it's zero by symmetry because of reasons that presumably you have thought through. The reasons are what I'm interested in. Give me the reasons, right? So that's one thing. The other thing is, when I was in college, invented a scam that this is connected to. And I don't want y'all to pull the same scam that I successfully pulled several times. Which is, to find myself on an exam, and I've got this integral to work out, and I just don't have time. There's a minute and a half left, and there's this integral that's going to take me several minutes, and I'm just going to put down equals zero by symmetry. And you'd be surprised how often that's true. Right? And I hadn't thought through the details. I don't know, time's running out. 6, 5, 4 equals zero by symmetry. And then I get points for it. Well, that was a scam. I didn't deserve those points. I shouldn't have gotten those points, right? So, being as aware as I am of this scam, right? I'm shutting the door on that scam, right? So that's another reason. You got to tell me why. By the way, now let's talk about how often does that come up? How is it that this scam works so effectively? And so this is an estimate that I'm going to give you, but I've given it some thought, consulted my memories from it was a long time ago, but still. And I think I'm going to say conservatively, 20% of the integrals that I encountered in my second major in physics that I did as an undergrad, about 20% of those integrals were zero by symmetry. That's a lot. If you think about how many classes there are in a physics major and take 20%, that's like almost 2 classes worth of integrals that are zero by symmetry. That's a lot. Right? So, and no surprise, the world's full of symmetries, right? The world is full of stuff that, like spheres, for example. The world's full of spheres, the world's full of circles. Symmetric, right? So it's a very common trick to be able to pull, and so you got to be able to give me some rationale. By the way, this observation I just made about 20%, that's also why I make a big deal about symmetry in Math 212. Because in your mostly engineering futures, engineering's not that different from physics, right? You're going to see a lot of integrals. And I can't say with any precision, but I would not be stunned if 20% of the integrals that you're going to see in the remainder of your undergraduate career might be zero by symmetry. Right? So there, I just saved you almost 2 classes worth of integration. Right? It's a really good observation. All right. Okay. So, but do be careful. Make sure to check the theorems. Make sure to check the conditions of the theorem. Make sure to give me the requirements that I need. Okay. Now there's a few physics applications in the book that we need to go through. This is not a physics class. However, the connection between the applications and the math is not that bad in these circumstances, and the connections between the physics and the math is nice examples of how Riemann sums can be applied in so many different ways. So it actually makes a lot of sense to talk about this in a math class, even though it's not a physics class. So here's the first one. It's called torque. I don't know if you're all aware of what torque is, but the idea is that if you have a point of support, right, and then there's a downward force such as gravity. Here's a little piece of mass, and there's a force downward. Well, easy experiment. Take a pen or something, push down on it right there with a certain amount of force. Feel how much twist you feel in your fingers, and now do the same thing over here. Right? Here's another experiment you can do. Take anything that you own that has a bolt on it. Grab that with your fingers and try to unscrew that bolt with your fingers. It's not going to work, right? And then get yourself a wrench with an arm on it about that long and effortless, right? So the length of that arm, how far when you're pushing, to turn something, how far you are away from the center of the turn makes it a lot easier in some sense, whatever that is, to turn the thing. Well, whatever that is called torque. Right? So pretty reasonable concept. And the formula for it is the force that's being applied times the distance from the point of support to where the force is being applied. Okay, so in this case, now we're considering a rod, and that rod is being supported at a single point, and I want to compute the total torque. Now, a weird situation, right? Because, well, this little piece of mass is pulling down, but it's that far from the center. This little piece of mass over here may be pushing down the exact same amount, but it's further from the point of support, and so it's applying more torque. Right? Well, grand total over this entire thing, there's a certain amount of mass, yeah, but all that mass is applying completely different amounts of torque because it's pushing down at these different locations. You're having different amounts of mechanical advantage. Does that make sense to everybody? Okay. All right. So the idea is, chop it up, add it up, our usual. And if you look at one little piece of mass at a time, there's a little piece of mass, right? Mass times distance gives you torque. That's the amount of torque that one little piece of mass applies. And per the chop it up, add it up strategy, add up a bunch of little pieces of torque, and that gives you the total torque. So this integral tells you the total amount of torque. If you have this metal rod, the point of support, and you want to know how much twisty power, right, is it being applied at the point of support? Well, there it is. Okay. All right. Now, a nice application of this is you can ask this question: what is the point? So where should I put my finger? Where does this point S that makes the torque 0? Why is this a natural question? Well, because that's the balancing point, which I'm no good at. So let's pretend I'm balancing that and not holding it, right? So there is a point at which the torque pulling it one way versus the torque pulling it the other way is exactly the same, and it balances. So this is a very physically natural thing. Center of mass is a common term. Sometimes it's called the centroid, right? But it's natural in the sense that this is where things balance, which if you don't want stuff to fall down, this is a good concept, right? Okay, so we have a formula for how to find that thing. We just set the torque equal to 0. Setting this equal to 0, separate the integral into two integrals, solve for S, and there's your formula for your center of mass. Okay. All right, and I'm going to rewrite this a little bit just for cosmetic reasons. I'm going to rewrite this M in the denominator as integral of 1 dm, that's mass, right? Total of the little pieces of mass. And that gives a nice way to remember this formula. We have integral dm divided by integral dm. It's just that you put an extra factor of x in the numerator. It's literally a weighted average of the x coordinates of the points on the shape in question. So that's how I remember it, by the way. Integral x dm over integral 1 dm. All right. By the way, if you're not sure what a weighted average is, it's I can talk to you about it. Come to office hours. I'll tell you about that. Okay. All right. Now that's a single variable version. This is a multivariable calculus class. What does it look like in a multivariable setting? Well, I argue that if you would like to know the point at which a two-dimensional thing will balance, right, like so, I argue that, that would be the intersection of the point where it balances this way and the point where it balances this way. Right? Because in other words, you don't want it to fall over in this direction, but you also don't want it to fall over in that direction. So, that gives you then two formulas. Where in the x direction? Well, it's a formula from the previous page. Right? Where in the y direction? Well, it's analogous to the formula on the previous page. And this gives you the coordinates computed one at a time for the centroid of a two-dimensional region. Now, do notice that for each one of these, let's look at the x-coordinate, we are still adding up over, we are still adding up over the entire region. It's still all of the pieces of mass. Right? So the domain is this entire region. So it is a double integral now. It's a double integral that computes the x-coordinate of the center of mass. And then likewise, it's a double integral that computes the y-coordinate of the center of mass. Also. Okay. All right. So example. Quick convention. If you have an actual physical thing that has actual physical mass, then density is whatever it is. But if you want to talk about a geometric shape, like if I say, well, this shape right here, and forget about mass and forget about physics, but just, sort of geometrically, what's the centroid of that region? So if there is no notion of density, just assume that density is 1. That's just a convention. All right. Okay, so here's an actual example, and so here's the upper semi-disk of radius A. Yeah. Now let's compute the centroid of this upper semi-disk. Notice we're not interested in mass. Density is 1. This is just a geometric figure. Okay, so here's the coordinate. Here's the formula for x bar. Now, two options. One option is you could take this double integral and subdivide, or slice it up and then slice up the slices, the usual, and crank it out with two antiderivatives. Or you can make a symmetry argument. I told you it comes up all the time. So here's an example. It's just the world's full of circles. It's because this thing is half of a circle that gives it that symmetry. Yeah? Okay. All right. Now think through the details on that. Now, if this was the question and you wrote this down on the exam, you wouldn't get the full credit because, well, look, you left out all the actual thoughts there. I mean, what you say is true but unsubstantiated, right? And so you got to give me the details. So think through those details, right? What has to be observed to conclude that actually is zero by symmetry? Okay. All right. Okay, let's find the y-coordinate. This is not zero by symmetry, mostly because it's not 0. Therefore, it's not zero by symmetry. This is going to be an actual crank it out situation. And y'all know how to do these. So I'm not going to spend a lot of time on this, but I do want to observe that this is one of those situations where it's kind of hard to see what the best way to slice is. Now, in the calculation that I've got here, right, in that calculation, you'll notice that I do my y slicing first. All right? It's not hard to see that y goes from 0 to a. Right? And then for a given y value, x doesn't go from negative a to a. Don't make that mistake. Right? X goes from, you got to write down those points. The points are on certain curves. What's the equation for the curve? Solve for what you're interested in. Those are the x bounds. I'll let you guys fill in those details. Then algebra crank. But look what happens if you do it the other way. Now, there's no particular reason, obviously, to slice one way versus another. In neither way that you slice will slice through corners. You're going to have square roots in your bounds no matter what. It doesn't seem clear that which way is the obviously right way to do it. And yet, look what happens if you slice the other way. Something nice, something hard to see coming. And that is, if you slice with your x slices first, right? And look at the y bounds. Y goes from 0 to a square root. Okay, so again, there's square root and whatever, who cares? But they did a little bit of good fortune. Look at that. I'm doing my first antiderivative is of y with respect to y. That gives me a y squared into which I'm plugging a square root. And the square root goes away. Dumb luck. Right? So just because I happen to put the dy there makes the outside integral easy. Whereas going the other direction, with the dx here, there is no y squared, and putting these square roots into the x leads to an integral here that's not particularly easy. I mean, it's fine. It's a substitution, right? But I think you'd have to give this to me. It's harder. Right? So I don't know how to advise you on how to make choices like this. There is no sort of obvious rule, but just try to anticipate these kinds of things. You do know that whenever you have circles, you're going to have square roots in your bounds. Square roots are obviously undesirable as an integrand. So maybe look at what your integrand is and think, how am I going to arrange to have its first antiderivative be something that square roots will plug in nicely into? So it's just I don't know. This is how one particular example worked, and kind of be on the lookout for this kind of thing. Yeah.
When we plugged it into the formula, why do we say that the area is equal to the mass? Is that?
Because density was 1. Yeah. Right. Yep. Does that make sense? Yeah. Right. So these formulas in general are right in terms of mass, and don't forget that mass. Where did I write that? Yeah, here it is. Mass is density times size, whatever appropriate to whatever the context is. Yeah. Right. Good question. Okay. So anyway, heads up on the algebra. I think this second alternative solution's a little bit easier. Easier integrals for sure. Same answer, of course. All right. Okay, Pappus's theorem. This is great. Books, by the way, very often write this as the Theorem of Pappus instead of Pappus's theorem, because no one's 100% sure whether there should be an apostrophe or an apostrophe S. Right? And so I've seen it both ways. I've seen books that write Pappus apostrophe, and I've seen books that write Pappus apostrophe S. It's subjective. I mean, in terms of pronunciation, if I make this a possessive, I say Pappus's theorem. And so I feel it necessary to write apostrophe S. But some people say Pappus theorem. It just sounds weird to me, like the guy's name was Papa. Which of course it wasn't. Anyway. You avoid the problem by saying Theorem of Pappus. A little hack. Okay, so here's the situation that we're going to address. Let's suppose that you have a plane. It doesn't matter where the plane is. I've drawn it floating in space. Not that it usually will be, but just to point out, this could be any plane, right? And then let's suppose you have a line in that plane, not parallel. It's got to be in the plane. And then let's suppose that you have an area that is both in the plane and completely on one side of the line. It can't straddle the line. Not allowed. Okay, so that's the scenario. Plane contains a line, area on one side of the line in the plane. Okay. And let's ask the question, what happens if I were to take this area and rotate it around that line, and it, of course, sweeps out a volume. Y'all have seen stuff kind of like this before. And how would I compute the volume of that thing? Well, Calc 1, right? You take slices, blah, blah, blah. Okay. So Pappus's theorem is the following observation. Let's consider one little piece of area at a time. Let's look just at that one little piece of area. And ask, when you rotate that one little piece of area around, you're going to get a little piece of volume, and it's going to be like a long, skinny, circular kind of tube. Right? All right, well, what's the volume of that? And if I know how much volume that generates when you rotate it around, And if I know how much volume this next piece generates when you rotate it around, if you just add up all the little volumes, none of these volumes will intersect each other. It's a very sort of weird way to effectively slice up this total volume. I can compute the total volume as the sum of the little volumes that I get when I rotate one piece of area at a time. And so that calculation goes like this. You have one little piece of area right there. That area times the total distance that it rotates around, which of course is just 2 pi r. If you think about it, area times distance should give you volume. Yeah? Okay. All right, so total volume is the sum of these little pieces of volume. Oh, hey, what happened there? Oh, my elbow touched this thing. Sorry about that. Okay, my bad. Okay, oh, that scared me. Okay. So yeah, there's an integral, and I suppose you can crank out that integral, but it's even better. This is where the move gets really slick, and that is to take this resulting integral here and factor out the 2 pi. And then both multiply and divide by area, weirdly. All right? And then look at this expression and observe that looks just like the formula for a centroid. Right? I mean, it's not exactly. I mean, this radius, this radius is off in some direction, right? But if I were to call that an r-axis and then, kind of turn your head to the side so it looks like the x-axis, that's morally equivalent, right? And so in that, not the x direction, not the y direction, but in what you might call the r direction, this is what you might call the r coordinate of the centroid. This is the distance then from the centroid to the line that you're rotating around. I guess I have to do that. So the formula simplifies then really nicely. That being just the distance. That being the distance from the centroid to the line, and then notice that this distance, if I say r bar, if I say r bar is that distance, then notice that what we have here, 2 pi r bar. I made a bad color choice, didn't I? Let me, that's green. There we go. R bar is the distance from the centroid to the line. 2 pi r bar is the distance around that circle. It's a distance traveled by the centroid. Which again, wrong color. And I get that formula. So it works out really nicely. Wonderful result that the volume is equal to the area times the distance traveled by the centroid. This is kind of almost a little magical result. Give me 2 seconds. So roughly speaking, what makes this work is that volume is computed by a double integral. And then we observe that, effectively, the distance traveled by the centroid is computed by a double integral, and it just happens to be that even though volume and centroid are geometrically different, coincidentally, except for a couple of constants here and there, they're computed by the same integral, very similar looking integrals. And if two things are computed by the same expression, then they're equal to each other. And of course, there's the extra constants to worry about. But anyway, that's morally sort of why this result works. Yeah, you had a question.
The centroid is the center point of the domain?
It's the centroid. So it's this thing here. It's this point that's defined by these integrals. And so, it's kind of the center point, but it's defined by integrals, and you can't just kind of pick it by choice. Yeah,
if the mass
that's right.
is spread out evenly, it's like the balance.
It's the balancing point. Yeah, exactly. Right. Exactly. Okay. Yeah, that's right. Yeah. Okay, so there are several examples where this can be used really conveniently. Here's one. Suppose you have this triangle, right, in the XY plane, and you want to rotate that triangle around that line. Rotate a triangle around a line. This sounds, flashbacks to Calc 1. Right? And this generates this, sort of volcano-looking thing there. Right? Volcanic cone. What's the volume of the volcano? There's this total volume here. Well, this fits perfectly into the situation, right? So all the rules are satisfied, and the volume that I don't know, right? This volume that I don't know relates to the how far did the centroid move of this triangle? And the triangle is pretty clear where the centroid is. Right, this centroid is, I'm going to say, obviously on the y-axis. And so the distance traveled by the centroid, well, let me say it like this. This is the radius of that centroid from the line in question. And so the distance traveled by the centroid is 2 pi times that. Right? The area of the triangle 1, and easy arithmetic. Okay, so in this formula here, volume equaling area and distance traveled by the centroid. Area is usually the easy one to compute. If you know where the centroid is, that'll help you compute volume. And by the way, vice versa. If you know the volume that you get when you rotate something, you can use that to find the distance traveled by the centroid. And here's an example of that. Where's the centroid of this rotating, of this semi-disk? And I remember that's the problem we solved on the previous page with 2 different competing integrals of different difficulty. One of which was slightly less difficult than the other, but it's kind of still, you got a bunch of stuff to write down. Well, when you rotate a semi-disk, you get a sphere. Spheres, I know the volume. So I don't know where the centroid is. That's the question that we're interested in. But I do know the volume. 4/3 pi r cubed, r being a in this case. Right? And then solve for y bar. And you get the same answer that we got by double integrals a couple pages back. So that's a pretty slick move. Yeah. So Pappus' theorem is not always use a centroid to compute a volume. Sometimes it's use a volume to compute a centroid. It can go either way. All right. Right. Okay. There is a second theorem of Pappus. I'm not going to spend as much time on this, but it's the same idea, except instead of having an area that you rotate to make a volume, what if you have a curve that you rotate to make an area? Not that different. Morally pretty similar. Chop it up, add it up. The total area is the sum of the areas that you get by looking at each piece of curve. Looking at one little piece of curve, the formula for the area is pretty straightforward. Length of that little piece of curve times the distance that it travels as you rotate. Now here's where I have to sweep something under the rug. You do the usual trick, pull out the 2 pi. This time we multiply and divide by length. Kind of analogous. And I have to sweep something under the rug here when I argue that this is the location of the centroid. And the distance of the centroid away from the curve. And the reason I'm sweeping something under the rug here is that we haven't talked about integrals over curves, really. Right? That's kind of awkward. So anyway, though, if you were to, it means exactly what you would think it means. It means look on the entire curve, on each piece of curve, write down the r, write down the length of that little piece of curve, add it up over the whole thing. So note that this expression structurally looks just like the formula for the centroid. I'm going to assert that it is. Right? You don't have to follow that. You can take my word on that. And we get this same morally equivalent result anyway. If you're rotating a curve to get area, the area relates to the length of the curve, again by the distance traveled by the centroid. And a nice example here. Suppose you're interested in this curve. Now, I emphasize, we're talking about the curve here. We're not talking about the disk. Right? No, not the yellow thing. We're talking only about the purple thing. Right, so this is what we call the upper semicircle, not the upper semi-disk. Right? It's the subtleties of the language are critical. Right? So circle means a curve. Disk means an area. Got to be careful with that terminology. So we're interested in the upper semicircle. We have yet to compute where the centroid of that is. Right, so where is that centroid at? Hard problem. We don't really know how to do integrals on curves. Technically, we can't even write that down, except we can make the following argument that, well, where that is, right, that y coordinate, it relates to the total area that you get by rotating that around, which we do know, right, 4 pi r squared, high school geometry, formula for the area of a sphere, right? Related by Pappus' theorem, we know the length of the curve, old news, the length of the curve, and go through, solve for what you're interested in, and there you go. Okay, is everybody on board? Did I go over time? I only went a minute over time. Okay, fine. Great. See y'all later. Yeah. Oh, I owe you an email. I got to look at the syllabus and check stuff out. But thank you for the reminder. I'll send that email out soon.